trig because of the unit circle.
Yeah, the very first slide says unit circle, so it's all about trig, right? Wrong. E for effort. It's all about geometry, kind of. But what kind of geometry? Like triangle, circle, square sort of thing?
Yeah.
Kind of. Starts with lines. Don't worry, we'll come back. Then it jumps to, let's see, we're section 10.2. Ooh. Ooh!
10-2.
What are these?
I don't know.
That's a good question.
Cool.
Conic sections! We did some of that last year, right? Hyperbolas? You didn't do any hyperbolas last year at all?
Yeah.
Wait, so we're starting with 10-2?
Okay, that'll be fun. And then we're going to go ahead and, no, don't worry, we're coming back to 10.1. Then we talk about ellipses and their foci, etc., etc. Then we talk about hyperbolas, which are some of the conic sections. Then we talk about quadric surfaces. That just sounds crazy. I don't know what's going on there. Long story short, we're going to be spinning stuff. And not spinning like trying to sell something in the sense of being dishonest. But all that comes back to section 10.1, which is lines. Eileen, the two on your chair were makeup ones from yesterday, so it's full credit, just like we did with honors. And then the other ones are pre-cal. They did 9.1, 9.2, 9.3, 9.5, review, 25 points. No 9.4. Okay. But before we get to lines, do you guys see the whole slopey thing? And if we keep on going, don't worry, I'll come back. Oh! Why is there trig? This tangent is just merely used in one of the formulas. That's it. No big dealio. It's not tons of trigs. Let's just really quickly review how you know the unit circle. Could you know the unit circle with the table?
Yes.
Sure. And if you did know it with the table, help me fill it in. How does it work? What sign is 0? Sine of 30. What's 30 in radians? We just did have pi. 1/6, right? Because 1/6 the calzone is less than 1/3. So we have pi over 6, and then we have pi over 4, and then we have pi over 3, and then we have pi over 2. But those are just what they are in radians, right? Okay, so hold on. So what is sine at pi over 6 or sine of 30?
Sine is 1 though.
1, 2, 3.
3, 2, 1. All 2, except for 1.
3, 2, 1.
Yeah.
Number 2. Square root 3 over 1. Square root of 3. 0 and undefined are randomly just in there, and so are the 1s and 0s. Okay, so let's not even talk about the signs. Anyway, this is all how to get the trig of the first quadrant, true? Remind me real quick, how do we get to other quadrants? Oh, yes you do. What are all the signs in the first quadrant? Positive, positive, right? All students take calculus. All trig functions are positive. How about second quadrant? What do we have? X's or minuses, Y's or plus, so therefore I heard sine is what? Positive. All students. Sine and his reciprocal, who is? Oh, secant. Right. The C's and S's don't go together. Third quadrant. Who's negative? Ah, who's negative?
Sine
Sine and cosine, and they're reciprocals. Secant and cosecant. Nope, cosecant and secant. Who's positive? And his reciprocal, who is? Cotangent. And then we have the x being positive, the y being negative. All students take calculus. Nice.
Oh, nice.
Look at him. Quite the entrance. C, what does that mean? Who's positive in the fourth quadrant? Cosine, his reciprocal, who is? Got it, let's go. 10-1. Luca, you missed it. Tonight, Google doodling infinite elephants. Doodling infinite elephants.
After this class, I'll get you last for them.
Don't be near as entertaining. Lines. Hey, what's the old-fashioned way of finding the slope of a line? Good. Rise over run, which we can tell we can find by measuring between any 2 points, right? Does it matter what 2 points we choose? What do you mean no? Isn't the rise over run going to be a smaller number if we do it over 2 closer points? The ratio will be the same. Good, nicely done, nicely done. So we do have an old-fashioned stuff is rise over run. How do we find it? How do we use like y's and x's to find it? That's like the algebra 1 way to do it. In calculus though, we could say x2 minus x1 and we could say f of x2 minus f of x1. Why would I put the formula that way perhaps? Sorry, it's small. Why might I use f of x in function notation instead? Yeah, maybe they don't give us the y values. Maybe they give us the function, and in order to graph, we need to plug in the x's to get the y's. Does that make sense? Might be a thing. But either way, rise over run. And why does an entire line only have one slope? It has constant slope. The slope remains the same. So the average rate from any 2 times or any 2 points on the line, remember average rate is the same thing as slope. The average rate will be the instantaneous rate, meaning the slope between any 2 points will be the same as the slope at any 1 point. That's all old school stuff, but now we have this new word called inclination, which maybe isn't that crazy. Inclination. What do you guys see in inclination? Not just like the grammatical sense or the English definition. Inclined. Now you could be inclined to do something, that would be the English way. But in math, what do you think an incline means? And we've seen it before. No. Not specifically. Exponential growth is going to have lots of different inclines and lots of different slopes.
Positive slope?
Maybe positive slope. Could kind of be negative slope also. Has anybody ever gone to Bakersfield?
Yeah.
Is there a big hill? Like right past Santa Clarita-ish? What's true when you see signs, road signs for big hills? What do they tend to tell you? And it's mostly for semi-truck drivers and their brakes and whatnot.
Like 3.5 tons, axle, 6 axle.
You can't plug in the road. You can go that direction a few times. Yeah, it might say incline, it might say grade, like the percent grade. It says something about like be careful. It usually has like a runaway ramp and it has like turn off your air conditioner, stuff like that. But anyway, long story short, incline. What does it mean in math or in life?
Go up.
It doesn't mean going up. It means how steep. Doesn't that make sense?
Yeah.
If it talks about a percent of the grade or a percent of the incline, it's trying to describe too, especially the semi-truck drivers, exactly how steep this road is so that they know what speeds to stay in between. Why is it especially helpful for semi-truck drivers and other ones who are driving big vehicles, especially heavy vehicles? What happens if their brakes overheat? They're in some big trouble, right? So they have to be careful in the sense of, especially on the downhill. They can't be going too fast or else they could get in some big time trouble and not be able to stop in time. Hence the runaway ramps. Anyway, coming back. Incline, how steep, right? So what do the notes say? The positive angle measured in standard position from the horizontal to the line. Incline. Inclination. It's the angle describing the incline. Describing how steep the incline is. And the reason I said no to exponential growth is what's the only type of function, type of graph that's going to have a specific incline?
Linear.
Yeah, just a line. Now maybe absolute value. Why would I say that? What's absolute value of x look like? He's the v, so he's kind of like linear on each side. So either a line or a function that's comprised, whose graph is comprised of lines. Now, what kinds of different inclines, inclinations, angles of inclination could we have? think vectors in the sense of, in order to have an angle of 0, it doesn't have to be down here on the angle of 0. It just needs to have an angle of rotation of 0. Does that make sense, guys? AKA, it just needs to be a flat line. Even if you were traveling on, what am I trying to say? What's it called on skateboard? Is it riding a rail? Is that right? When you're going across a rail? That's removed from the ground, right?
Shredding them on.
You just don't know where it's going. You pop up the skateboard on top of like a stair rail or something, one that's straight across.
Oh, pop an ollie.
Oh, there you go. Sure. Okay.
That's not it, that's not it.
I don't think that's it. I'm just,
Okay, Sean, I see you.
so no borders in here.
You're not taking me to the beach, I'll say.
Alright, so let's pretend, you guys,
I love this class.
let's pretend we have a rail, okay? And let's say you go up on your skateboard, but I don't think any of us would do that because I'm not so sure we can do that because we don't even know how to talk about it. Anyway, so, and you're riding it, right? Question, are you off the ground? And the question is, yes. However, what is your inclination of what you're doing right now? Are you going uphill? No. Are you going downhill? No. But you're off the ground. I don't care. What's your angle of inclination? 0. You're just going straight across. Does that make sense? Now, if you're trying to do this down some stairs, that's an incline. True? Okay. So then coming back, angle of inclination, even if it's not on the x-axis, as long as it's flat, the angle is 0. Other than that, any of the other angles, we can think about measuring with the horizontal axis. But guys, if I measured a different horizontal, couldn't it be the same incline if you're measuring that angle? What do we know about parallel lines? And a transversal that cuts.
Congruent.
And what would be true about these two angles?
They're equal.
Yeah, wouldn't they be the same?
Yeah.
True. So, when we're talking about angle of inclination, you can think of it to the x-axis, but you can also think any horizontal line is going to be the exact same angle. Cool? So we have an acute little angle, right? We have an obtuse little angle. Even if it's not like over here specifically, it's over here randomly, but it doesn't matter. It still has an obtuse angle of inclination because that's how rotated it is. Can I kind of say it that way? That's how rotated it is. So let's keep going. There is another formula for how to find slope, and it all comes back to trig. There is another formula for how to find slope. Let me go ahead, and as you guys are writing down the formula, let me get a quick picture of what we were just seeing on the other page. That if we have, for instance, an x and a y, and we have some random line that we're trying to find the slope of, if we can find the angle of inclination, if we can find a theta, and we're talking about a line, guys, we can go back to trig. Look at us, we can take all sorts of things back to trig. How can we take this back to trig? If we have an angle and if we have a line, what can we make out of it, kiddos? A triangle. And we would have an opposite side, true, and we would have an adjacent side, true. The question, thinking about slope, what would the opposite and the adjacent be synonymous with? Exactly. So we can think of the opposite as also being the rise. The length of the opposite can signify or be the rise, and the length of the adjacent could be the run. So let's see if this formula can make some sense. M equals rise over run. Why is that tangent? Oh, come on, you got this. Exactly. Tangent is opposite over adjacent, right? And if tangent is opposite over adjacent, what can we use with our new synonyms? Rise over run. Does it make sense how M is really tangent? Ooh, that just got exciting because we've only talked about really this year slopes to lines or slopes of lines. But if slope means rate, If you travel in a line, is that the only way that you can be going a certain speed? No. You could travel in curves, you can travel in wiggly lines, you can travel in sinusoids. You can travel in all sorts of ways, or movement can happen in all sorts of ways, not just lines. So maybe this opens up a whole new world of another definition of slope. Slope is tangent of an angle. Now, the angle is just going to be the angle of inclination. Let's go ahead and fill it in. Angle of inclination. And m is just going to be the slope, as we already know. Theta is going to be the angle of inclination, and m is going to be the slope. Now I'm trying to introduce you to a few ideas we'll see a little bit later. We've talked about how only linear functions can have one specific constant incline. Does that make sense, guys? Because wherever you are in a line, whether you're here in a line going up, whether you're here on a line going up, you're still going to have the exact same incline, right? But question, what if you were going up something like this? Are you still going up? Yeah. So couldn't we call it an incline?
Not consistent.
How do you do slopes to something that's curved? Calculus. How do you do slopes to something that's curved? Well, you can't just use one angle of inclination. But in geometry, didn't you learn something to do with tangents and something curved, aka a circle? What did you learn about tangents and circles in geometry?
Getting, when the line passes through.
When the line
that point.
passes through one point?
One point.
Let's say skims at one point. Passes through, I'm thinking of a secant line. Does that make sense from geometry? So, when a line passes through, let's say you're here going up. Specifically, at this place, it's still curved, right? Can I zoom in anymore? Oh, I really can't. I'm trying to. Even though you're still traveling on a curve, question, kiddos, at that instant, couldn't it kind of feel like you're at this incline? At that instant. Even though the entire path is curved, couldn't you be feeling the pressure of this incline? Yeah. What is this? A tangent line. Guess what we would say is the slope at this point? The slope of this tangent line. Now, how do we find that? That's the struggle. We don't know yet. How come? Because you're not on the tangent line. Well, you are, but you're only on the tangent line at how many points? 1. How many points do we need to find slope? 2. Well, how do you find slope with only 1 point? Subtract it from itself, y1 minus y1 over x1 minus x1. Isn't that going to be 0 over 0? What is 0 over 0? Give me an answer. Just guess. 0 over 0. Not necessarily. But sometimes. Give it another guess. What's 0 over 0? 1? Not necessarily, but sometimes. Give me another answer. What's 0 over 0?
0.
Not necessarily, but sometimes.
No.
0 over 0 does not have one set answer.
Oh, Missy, don't mess with my brain like that.
There's another way to do it, and it's called using limits. Oh, we did that last chapter. Okay, let's stop. We're not in calculus yet. That's chapter 12. Okay.
Who's got some Advil?
Oh, come on. You didn't even watch the Infinite Elephant video.
Yeah.
Okay, coming back. Long story short, we're not dealing with curves. Even though it's good for calculus, it's bad for us right this second. But the cool thing is, in this chapter, we actually are going to be able to do the slope at a point of a parabola only. It's going to be kind of complicated, and it's going to make us thankful for calculus in chapter 12 when we get there. But we're not starting there. We're starting with lines. So kiddos, if they give us a problem like this, we have m equals tangent of theta, and for a line, there's only one theta that we have to worry about, only one incline. How would we do this example? Find the inclination of x minus y equals 2 and 2x plus 3y equals 6. Separately, two different problems. How would we start with A?
the slope intercept, so that we can find the actual slope and just put it in.
Yeah, we can find the actual slope. What's Sean saying? Get the y by itself. How quick can you guys go? X plus 2? X minus 2, right? But hold on, that's not the inclination. Inclination, they're specifically talking about the angle, right? The angle of inclination, how inclined, how steep. So what can we take from this rearrangement? We can take, yeah, the one in front of the x and call it m. Now what can we do with that m?
Set it equal to the tangent of the theta.
Exactly. So set r1 equal to tangent of theta. Let's pretend this was a no calculator part. How do I solve for theta? Inverse tangent both sides? That sounds fun.
1, 2, 33, 2, 1, everything. 33 over 31, 45 degrees.
What did he just do? He got to the last row of his table and he said square root of 3 over 3, 1. Hey, tangent is 1, but where? In the middle. Where's the middle? Pi over 4. So we could say theta is equal to 45 degrees or pi over 4. I believe in this one, kind of like the physics-y, vector-y section, I believe degrees is acceptable. That's never a bad thing to keep radians in, since calculus is only in radians.
And what's nice about this is the slope already gives you the quadrant.
Yeah. Wait. How did Luca figure that out? The slope already gives us the quadrant. What's he mean by that? What if we were to graph this line, guys? How would we graph y equals x minus 2? Good, negative 2 would be our b. Then what? Up 1 over 1, up 1 over 1. What angle are we looking for? If possible, the little acute one. Go find the x-axis and do the little acute one. 45 degrees, right guys? Do we want 225? No. Could we have done 225 and it also hits the line? Yes. But we want the little acute one. We want the simplest answer possible. Okay, kiddos, that was only letter A. How do we do letter B? Same dealio. How quick can you guys go? Solve for y. What do you guys think? Cool beans. What do we know from that? M equals who? How do we solve for our angle of inclination, our theta? So equal to who? And how do I get to theta? Tangent inverse of both sides. If some of you guys didn't follow what I did, I'm taking tangent inverse of the right, taking tangent inverse of the left, tangent inverse of tangent, ultimately cancels out. And we can say theta equals tangent inverse of negative 2/3. That's not a unit circle one, right? Square root of 3 over 3, 1 square root of 3. Nope, it's none of those. Or 0 undefined. Calculators. Plug and chug. I told you guys think in degrees. I'm pretty sure angle of inclination, that's more physicsy, that's more like real lifey. Actually, calculus is real life, so is radians, but
Negative 33.7.
ew, do we want to keep a negative 33.7? Pause, let's go back and look at inclinations real quick. How did they measure all of these inclinations? From standard position, aka positively, right? So if our calculator gives us a negative, what are we going to do, kiddos?
180.
Yep, plus 180. Remember, negative 33 is in the fourth quadrant. We can make it in the second quadrant if we just add 180. And if you're like, that's sketch, we're not quite so sure about that. Sketchers? Oh no, Chapel guy talked about Converse. Wrong one. Either way, -2 over 1 and a 2 and a 3. Probably some of your parents wear Skechers to work, especially if they're on their feet all day. Why would I add 180? Yeah, do you see how the -33 is going the wrong way? Which way do we want to go? Not that way. We want to go that way. And kiddos, what do those two have to add up to? 1. Well, 180 they both add up to. That's why I'm adding the 180 to the negative. And you guys got 310. Can we just round to 0.3 then?
Yeah.
Cool. Dun 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 dun. So that's an obtuse angle of inclination. Don't go negative, go positive. Take the negative, use it, but don't keep that as your final answer. That's it, right? What happens if they give us the inclination and they want us to find the slope? What if they say theta is equal to 50 degrees? Oh, well that's easy, right? This isn't bad. Because m is equal to tangent of theta, so we just plug in 150. Why would this be a non-calculator problem?
Because we already know tangent of 150.
Because remember, 30, 45, 60. Question, what's 180 minus 150?
1 square root of 3. Negative square root of 3.
Yeah, remember 150 is just 30 away, true? From 180. So therefore we're going to use square root of 3 over 3, 1 square root of 3. However, question, positive or negative?
Negative.
Because it's in what quadrant? Got it. So is it going downhill or uphill? And doesn't that make sense if we were to graph 150? What kind of line do we have? Downhill. Does that make sense? We have a downhill graph. Okay, so it doesn't get any worse than that, right? Ooh, what if they ask us this one? Find the inclination given 2 points on a line. What's the formula for inclination? M equals tangent theta. They don't give us m, they don't give us theta, but they do give us how many points? And what can we do with any 2 points on a line? Yep. Find the slope. M is equal to... Does it matter which way we go as long as we go away and keep it consistent? Keep it consistent. You can choose the first point to be x1, y1. You can choose the second point to be x1, y1. Just keep it consistent. Some of you won't like it, but how do we combine square root of 3 minus 2 root 3? Yep, they're like terms. Like 1x minus 2x is negative x. 1 root 3 minus 2 root 3 is negative 1 root 3. All over 0 minus 1. Change to positive. So m is equal to root 3, which equals tangent of theta, square root of 3 over 3, 1 square root of 3. What's theta? 60 degrees. Do you guys see how they can talk about slope, talk about inclination, have you work with the formula lots of different ways? But none of them are impossible. Just makes you think a little differently about what you're supposed to be finding. Here's how it can get just a little bit funnier.
The thing is, every time I see inclination, I think of an angle.
Good. Because incline, right? Oh, is that a bad thing?
No, I might just like, oh, yeah, as for the inclination, I think it's the angle.
Oh, the angle?
Yeah.
So you find it. But you have an incline that you're working with that has an angle like built into it. You just have to figure out what it is from our formula. Huh. Done. Ooh, that was a first. I know.
I like that.
See, you came by to visit recently. I missed it. That's why it's been on the night.
For this problem, isn't it just subtracting the difference
Of what?
of the angles? Because we can go to slope intercept, get the slope, which is m, find both thetas, and then subtract it to find the difference.
I agree.
So here's his hypothesis. Subtract the inclinations, the angles of inclination. Alright, let's do it. Let's see if it works. His idea is subtract the inclinations.
Which one do you put first though? Subtracting for the other.
Well, angle between, let's just keep it this way. If we're trying to find between two objects, think geometry, we're keeping it positive. Like how with area and perimeter and things like that, we kept it positive because it was measurable. Let's do the same thing with this. Keep it positive. So if we have two lines, if we have to keep it positive, then we kind of have to figure out a picture of both, right? All right. You guys getting y by itself real quick? Because we need to get our ends, right? How's it look? Maybe I should show. So we have line number 1, we have line number 2. I'm going to go ahead and color code just for sake of simplicity. Let's make one of them blue. Just have fun with it. So we have y equals negative 3/4 x plus 3. We come on down for this one, we have to go down 1 and a 2 and a 3 and a 4. This one has to go up 1 and a 2 and a 3. 1 and a 2 and a 3 and a 4. 1 and a 2 and a 3 and a 4. Let's see if that's that. So for the red one, we have negative 4, up 2 over 1, up 2 over 1, up 2 over 1. Ah, that's roughly. Make it roughly linear. Okay, look good? We could find his angle of inclination using what? Good. N, which is 2, equals tangent of theta. Could I get some of you guys working on what that theta is? Because it'll be tangent inverse of 2, right? When we solve. That's a positive, so it should give me his inclination, which would be the red theta right here. Some of you guys might be plugging and chugging that one. We're going to go ahead and graph the other one. We start at positive 3. We go down 1, 2, 3 over 1, 2, 3, and 4. Down 1, 2, 3 over 1, 2, 3, and 4. Roughly, right? When we go to find our theta, when we set negative 3/4 equal to tangent of theta, question, are we keeping the positive or the negative? Good, we just want to keep on going positive. So we're going to say that theta is equal to tangent inverse of negative 3/4. Won't that hopefully find us this angle? Sure. Okay, cool. Now what? What'd you guys get for tangent inverse of 2?
I got 63.43 degrees.
You're going to back them up? Okay, let's go 3 decimal places though. So 63 point. How about for the second angle?
143.130. Yep.
How do we find angle between? Subtract. Seems to make sense, right? Because if we subtract, what are we going to get? Angle between. Angle between. So we can go ahead and subtract the 143.130 because we went ahead and solved for it. We can see the bigger minus the smaller angle between. The 143.130 minus the 63.435. And what do we get? 691?
695.
Okay, do you see how we kind of had to make a picture for both?
Yeah.
And find inclinations for both. We had to make sure that we were like subtracting the right way. Wouldn't it be nice? Look at you guys. No way. Wouldn't it it be nice if we had a little formula to use instead? So, do you think we could have solved this another way? It's the exact same problem. Would we still have had to find our y equals our n's for each?
Yeah.
Yeah. But how would we have used our n's? What would n1 have been? 2. And what would n2, once we solved for, what would n2 have been?
Sorry about that.
And what would we have done with both of those values?
Yes.
Get them in there. But wait, are we done once we plug them in there? What are we going to do to both sides? Wait. Take tangent inverse of both sides. Then would we have found the same angle? You guys are going to test it in homework, because wait, look. One more example and we're done. Do section 10-1 for tomorrow. Let's see how it goes. You just missed one little homework example. Bye guys.
Should I just put this on your desk?
Yeah, if you're done with this, put them in there.
Okay. That wasn't as bad as I thought it was. Wait, what? The R. Was it?
The one was circle.
Yeah, what was the circle?
I've been doing it the same time.
I think so.
You can bring headphones in if you have them. Oh, just like a reminder, you can take it late. I'll see it in the morning. I'll see it tonight. Because I can see the timestamp. So as long as it's by midnight. Oh no! Yeah, it's like, so all chapter 9 is like just missing.
Yeah. I need this one.
Oh, she was absent.
Oh.
So we're supposed to read chapter 8. Okay, we'll get it.
Okay.
Thank you.
Yeah. I have a question.
Yeah. Pause the video real quick.